Okay, so yeah, we are waiting for the battery for the mic, but before then, yeah, I'll just speak loud. So we stopped here at this base rule. So as I mentioned last time, the base rule allows us to change the process of generating those random sampling processes. So let's see. Okay, so considering this conditional probability where B happens after A happened, right? So in this case, we assume A already happened, and then we consider the probability of B is happening, and then that probability is represented in this, right? So it's basically the joint probability in the numerator divided by the probability of A. Okay, so yeah, so in this case, if we consider the probability of P of B3 given A, and then in this Venn diagram, the probability of B3 is this triangle, right? So the ratio of this area compared to the overall area of this rectangle, right? So that's the original probability of B3, but we now consider this conditional probability of B3 given A. So only within the region of A, which is this blue circle, we consider the ratio of this area within this part, between this part and this entire circle. Okay. So that probability is the ratio of. So basically, the area of this guy is represented as this. The probability of A and B3 jointly or simultaneously happening, and then the denominator or the overall area for P of A, which represents this circle, yeah, that is dividing this guy. Okay, so that way we can compute this guy. So from this definition of this conditional probability, this can be rewritten in this form, and then basically this equation allows us to change the orders of this generation process of A and B. So here in this case, the same joint probability of A and B simultaneously happening. So A and B simultaneously happen together, and that process or that probability can be considered where A first happened, and then after A happened, and then B happened, and then on the other hand, we can think of B first, and then after B happened, we can consider the probability of A given B. Okay, so so this is the main equation that we use for this Bayes rule. So specifically, the Bayes rule. Yeah, again, if I write it again, and then this guy is A and B and A, and then the the numerator. 고마워요. Okay, so so in this case, yeah, we can further rewrite the numerator in this form: A given B times P of B, right? So that way, this joint probability can be rewritten in the kind of reverse steps of. So first here we generate B first, and then after B happened, we consider the situation where A happened. So compared to this guy, where A happened first, and then B in the later on, and then in this probability we actually changed the order of A and B. Okay, so that's the practical kind of advantage of utilizing this Bayes rule. Okay, and then in this specific equation, what this equation is saying is that given A, we consider the conditional probability of B, for example, B3. Okay, let's suppose just R equals to 3, and then this conditional probability is just rewritten as B3 and A simultaneously, right? And then P of A, right? So this is directly coming from the definition of this conditional probability, okay? And then this guy is changed in this form. So we consider BR first, and then A given BR, and then in the numerator, so the denominator P of A can be rewritten as P of B1, P of A, okay. B1 and A plus P of B2 and A, and so on. Okay, so in that way we can compute this P of A. So in this case, writing this guy into this form can be understood from this figure. So let's suppose we want to compute the area of the circle, okay? But we are not given immediately the value of P of A. So we don't know directly about what the P of A is, but this P of A, or this blue circle, can be decomposed into this form. So the first part is this guy, and then second part, and the third part, and the fourth part, and so on. So P of A can be decomposed into multiple pieces, right? And these pieces is actually the same as, so this part is the intersection of the set A and, okay, and this guy, instead of a dot, let's consider it as B6, okay? In this case, A intersection of B6, right? So this region can be represented as this guy, P of A and the intersection of A and B6, right? So that way, the total area of A, or this blue circle, can be represented as the summation of all these intersections of A and each of B1, B2, and B3, and so on, right? So that way we can compute this P of A, even though P of A cannot be directly computed all at once. Okay, and then each of these terms will be represented, or can be rewritten as this form: P of B1 times P of A given B1, right? So that way, even though we consider this conditional probability, where A first and B3 later, but in this case, we considered B first, and then we considered A in the next phase. So that is the base rule. Any questions? Okay, then, yeah, let me just give a few comments about how these base rule and this kind of changing the the orders of the process of generating A and B and A. So these have really a practical impact or practical advantages when utilizing these methods when like doing the machine learning and artificial intelligence or other statistical data analysis. So, for example, when we consider the documents and their topics, so there is some method called topic modeling. And so in this case, suppose you have like thousands of news articles that you see in Naver.com, for example. So earlier today in the morning, we found that 1,000 news article just came out just this morning. Okay, and then they can be categorized into different topics in terms of their content. So some of them could be related to like economy, and some of them could be like related to electronics and science. Something like Galaxy 7 getting recalled and so on, right? So they have their own topics for each document, right? But in this case, we can, from the probability sense, we can consider this the generation process of one document. So suppose you are just a writer of an article, and then you will just write these articles based on what you think, right? But from the probability sense, it can be viewed as generating each word with based on a certain probability distribution. Okay, but in this case, suppose so in terms between the topics and their specific article. So for example, the broad category can be just on science and technology, and then a specific example of an article could be like a recall of this Galaxy 7. Okay, so in terms of these two, between these two topics, it's natural to think about the topic first. These types of process is kind of really a fundamental process or key idea for this something called likelihood and prior and posterior. Okay. So in this case, let me give just another example. So suppose we have to generate some samples from some Gaussian distribution. So you are all familiar with the Gaussian distribution, but before sampling the data from Gaussian distribution, we have to know what basically the parameter of the Gaussian distributions, which are the mean and the variance, right? So we have to first consider the mean and the variance. So P of mu and sigma squared, which represents the mean and variance. Okay. So suppose those two parameters were also sampled from their own distribution, and then, for example, mean equal to 3 and the variance equals to 6, for example. Suppose those 3 and 6 were sampled from some distribution, okay? And then from this distribution, so roughly it is like the mean here is positioned, and then the variance is around 6, right? Okay, so from this distribution, we can easily compute, for example, the data being sampled as maybe 5. So our actual data was sampled as 5, okay? So in that case, we can think of this process as this conditional probability, right? So those were our random variable, that were sampled in this stage, okay, before this process, okay, and then after that we sample X, right? But typical situation or problem is that suppose our data, I mean the set of samples that we obtained was like 3, 5, 8, and 5, 6, 7, 4, 3, 5, and so on, right? So all we know is these X values without knowing mu and sigma squared, right? So the typical problem in this probability and statistics is that we have to estimate or we have to guess what these mu and sigma squared are, right? So that way, in this simple example, these generation process is just reversed, right? So we have to first know mu and sigma squared in order to generate our samples, which are these values, right? But typically, what the problem that we have to solve is involving this reverse process or reverse generation process, right? So that way, we have to obtain this guy, mu and sigma squared, given X is these values, right? So this guy, okay, this guy. So given we observed these data, what is the probability distribution of mu and sigma squared? Well, intuitively, what should be mu? So mu should be somewhere around the mean of these values, right? So in this case, what is the mean? Suppose the mean is like 6.5, okay? But in this case, mean could be, or this mu could be 6.5, but they can have some other values, right? It could be a little less than 6, or more than maybe 7, and so on, right? So these mu values can have their own probability distribution, but from these data or these observations or these clues, we know that this mu is probably somewhere around 6.5, okay? But not exactly. So we can first consider this probability distribution or conditional probability distribution, and this one is called posterior because it's like changing the order, or it's considering the reverse process where this data first and then the parameter in the next step. Okay, so yeah, I cannot spend more time on this topic, but probably you will learn or study. You will at least a few opportunities to learn about these things. So these are called prior, and these are called likelihood, and this one is posterior. And then in terms of their relationship from the Bayes rule, okay. So back to the Bayes rule we just learned. We can think of this equations between these three terms, which are, so this one is something like P of A given B, okay? And this guy is P of A, and this part is P of B given A. So A is parameter, B is our data. So A and then to B is the natural order, and this guy, B then A, this type of an order is a reversed order. And then in terms of their relationship, it's just boils down to this Bayes rule of this guy. P of A times P, B given A, divided by P of A. Okay? So we only ignore this part. So up to this point, this and this and this, we still need this part in order to make these two parts equal. But in this case, typically we do not care about this. Yeah, so if we ignore that, then we can change that as, instead of being equal, we can make it as a proportional. Okay? Yeah, so these types of things will be what you will learn maybe in an year or two when studying in this school. Okay, so 네. 이게 우리는 그 전에 예제에서는 그 파라미터, 그러니까 뭐 저기 평균과 분산을 구해봐라라고 하는 문제. 데이터가 보통은 이렇게 주어져요, 그죠? 그래갖고 여기서 평균과 분산을 구하시오. 근데 평균과 분산을 구하긴 했지만 우리 데이터가 실제로 정확하게 그 평균과 분산을 이야기해주지 않을 수도 있죠, 그죠? 이게 좀 운이 나쁘게 평균은 한 2밖에 안 되는데 진짜 뭐 어떻게 해갖고 이렇게 큰 밸류들이 이렇게 뽑혀져 나왔을 수도 있는 거예요, 그죠? 그래서 우리가 데이터로부터 평균과 분산을 우리가 guess, 그러니까 짐작을 하지만 그 밸류가 정확하진 않을 수 있는 거죠, 그죠? 그래갖고 고등학교에서도 아마 그런 뭐 confidence interval이니, confidence interval이 뭐였죠, 영어로? 네? 그렇죠. 신뢰 구간 같은 거 배우잖아요. 네, 그래서 그런 신뢰 구간이 데이터가 더 많아지면 많아질수록 신뢰 구간이 굉장히 좁아지고. 그러니까 데이터가 이게 여기서 나타난 평균은 6.5인데 이게 한 데이터를 100개, 1000개에서 모은 걸 가지고 구한 평균은 한 그래도 0.5예요. 그렇지만 이 두 개가 똑같이 다 0.5라고는 이야기는 하지만 굉장히 그 두 개가 우리한테 이야기해주는 어떤 신용도는 완전히 다른 거예요. 데이터는 6.5라고 얘기긴 하지만 그게 8일 수도 있고 10일 수도 있고 아니면 2일 수도 있고 이런 게 이제 신뢰 구간이었었잖아요. 그죠? 그랬는데 그 신뢰 구간이나 이런 그런 실제로 우리가 파라미터를 구할 때도 데이터로부터 실제로 파라미터를 구하지만 그 데이터의 그런 어떤 신뢰 구간이라든가 그런 걸 통해서 이런 파라미터에 역시 마찬가지로 디스트리뷰션을 생각을 해볼 수가 있어요. 그러니까 신뢰 구간이라는 게 기본적으로 데이터가 10개 있었을 때는 뮤라고 하는 놈은 6.5를 기준으로 이렇게 좀 분산이 넓은 디스트리뷰션을 가지게 될 거고 100개의 데이터를 가지고 신뢰 구간을 우리가 따지면 그 뮤라고 하는 디스트리뷰션은 역시 6.5를 기준으로 굉장히 이렇게 좀 샤프한 이런 디스트리뷰션을 가지게 될 거예요. 즉 6.5보다 멀면 멀어질수록 그 확률은 급격하게 확 떨어진다는 거죠. 왜냐하면 데이터가 그만큼 우리한테 많은 신뢰도를 줬고 그랬기 때문에 이 분산이 굉장히 작아진 거예요. 그러면 결국은 어쨌건 이런 식의 개념에서 우리가 생각해 볼 수 있는 거는 뮤나 시그마 스퀘어, 이 분산이나 평균이 어떤 얘네들만의 probability distribution이 있을 수가 있다는 거고요. 얘네들의 어떤 확률 분포를 생각을 해볼 수가 있다는 거고 그 확률 분포가 데이터가 아무것도 없을 때에 그냥 얘네들이 갖고 있을 수 있는 어떤 probability distribution이 있어요. 그러면 그게 바로 뭐냐면 이놈이에요, 이놈. 어떤 단서도 없을 때. 그리고 이거는 개념적으로 뭐냐? 데이터들이 이렇게 주어졌어요. 그러면 그 데이터들이 주어졌을 때, 그 상황에서 그런 어떤 부가적인 단서가 있는 상황에서 이 뮤라고 하는 거, 그러니까 실제로 이 데이터가 가지는 평균이라고 하는 값의 이 디스트리뷰션은 뭘 거냐? 그런 이제 부가적인 정보가 추가된 채에 생각할 수 있는 조건부 확률 혹은 컨디셔널 프로바빌리티가 있는 거예요. 이 두 가지 개념이 있는 거죠. 그 다음에 요 가운데에 낀 요거는 이제 아까도 얘기했던 그러니까 자연스럽게 우리가 생각해 볼 수 있는 그 파라미터가 딱 정해지면 거기서부터 생성되는 그 가우시안 디스트리뷰션으로부터 생성되는 x들이 이렇게 잔뜩 있을 수가 있는 거고요. 그래서 하여튼 요 세 가지의 요소들이 굉장히 많은 어떤 알고리즘들에서 굉장히 중요한 역할들을 하고요. 그런 게 뭐 딥러닝이나 아니면 뭐 기타 여러 가지 머신러닝, 인공지능 뭐 이런 류 아니면 뭐 통계 방법들에서 가장 근간을 이루는 어떤 요소들이고 얘네들에서 베이지 룰이 해주는 역할은 순서를 이렇게 샥샥 바꿔준다는 거. 그래서 보통 우리가 구해야 되는 어떤 이 부분은 그 데이터가 실제로 제너레이트 되는 과정에 어떻게 보면 좀 반대라는 거. 네, 그래서 뭐 하여튼 이름으로는 요 놈을 이제 posterior라고 불러요. posterior. 그 다음에 이놈은 이제 likelihood라고 부르고 이놈은 이제 prior라고 불러요. 하여튼 이름이 뭐 그렇다는 거고요. 네. 그 다음에 이게 질문이 답이 됐어요? Okay, so let me just add a few comments. So this kind of a process of reversing the data generation order is quite common, and also as I briefly mentioned about the deep learning. So those deep learning have multiple layers like this, right? So these are input layer and these are output layer, and then these are kind of internal layers. Okay, so in this case, the typical problem setting is that so we want to estimate or predict a person's life expectancy, or like when this guy will die, right? In what age? Okay, I don't know who this guy is, but we have to estimate or predict this kind of a life expectancy based on their height and weight. So how tall he is and how, like, how large he is. Okay, so using these two values, we have to just guess or estimate the life expectancy of that guy. Okay, so in this typical setting of this machine learning and artificial intelligence, the input data that we supply to the model is given at this position. So removing this guy, so this is a height, and this is weight. Okay, and then at the end, so we only consider the single node, and this is a life expectancy. Okay. Okay. In this case, so it could be this kind of model can be just built just directly connecting those two values between input and output, where there's no other internal parts. Okay. But in these days, the deep learning involves many like hidden or internal layers. So we introduce these additional variables. So they are processed or transformed into these internal nodes, and then these internal node will generate another internal node in the next stage, and then finally those values will generate these final values of our life expectancy. Okay. So in this case, we have to teach our machine, or we have to train our machine or algorithm or this model, right? So all the data, in order to teach the machine, all the data that we give to machine is that this input and output. Okay. So in the past, one guy that is like 180 centimeter tall and 70 kilometer weight. Okay, that guy lived until maybe until the age of 70. Okay, and then the shorter guy, like 170 centimeter and a little lighter guy, like a 60 kilogram. That guy lived up to 80 in his age or her age. Okay, so those examples are provided so that we can train the algorithm. Okay, so those are typical settings. So we only give, in this model, we only give this part and this part as an example to train our model. So we have to estimate those internal parts, but as you see, the generation process is actually starting from the left to the right, right? So here already we have, this involves the process of this reversed order of process. So given this value that we know, so all we know is this part and this part. And so we have to know this part as well in order to properly train this model. So in this case, we typically reverse this order from from the right to the left, right? So that way it's already this kind of a reverse order, and technically this process is like a back propagation, if you're familiar with it. Okay, so although in this specific deep learning example, these are not probability models, so they don't specifically use the Bayes rule, but all the intuition are basically the same. Any other questions? Okay, then let's move to chapter 3. 챕터 3만 없네요? 그러네. 챕터 4 할까요, 그러면? 아이고, 이런. 잠깐만요. Okay, so the chapter 3 is about the random variable and probability distribution. So hopefully it gets more interesting. So first definition that we have to study is about this random variable. Okay, so random variable is basically some function. So in the case of function, it should have the input and output, right? So that's the main kind of component that forms this function. So in this case of function, what is the input and output? So input is each outcome or each element in our event space. Okay, so what was the event space in the world of a probability? So all the possible cases that we can observe and their set of all these possible outcomes are called event space. Right? So in the case of rolling a dice, the event could be like seeing 1 and seeing 2, 3, and so on. So we have in total 6 different outcomes, and each of these elements will form our event space. So each of these events will be our input for this function of this random variable. And then the output should be some number. Okay, so that is the definition of random variable. And then also in the, so it's basically like enumerating process. So when seeing the dice as a number of 5, and then we actually map them into a certain, another certain number. Okay, and also in the case of like flipping a coin, so we observe head and tail when flipping a coin, and then these are event space, and each of this outcome will be mapped into a particular value. For example, 1, 2. Okay, so this can be viewed as our random variable. For example, like x. Okay, so we can call that random variable x, and that actually maps this head from the flipping a coin process. We map this into 1, and this tail as 2. But in this case, what if this guy? So how about this type of mapping, where both of h and t is mapped to just same 1? In this case, can we call that as random variable? Or, in other words, can we call that as a function? Is it a function or not? Function, yes. It is not a function. It is function. Okay, it is function. Okay. So the random variable can map different outcomes into the same same value. Okay. So all the requirement for this function is that those values should be some numbers. Okay. So that is only a constraint. So in this case, in the case of dice rolling, 1, 2, 3, 4, 5, 6, and then our function or random variable x can map 1, 2, 3 as 0 and 4, 5, 6 as 1. Okay, and in this case, this random variable x has the meaning of whether the dice number is less than 4 or greater than or equal to 4. Okay. Okay, and then so in the previous chapter we learned about the sample space, and then this sample space can be categorized into two different things. So the first one is a discrete, a random sample space, and then the other is continuous sample space. So in the case of discrete sample space, basically the elements that we have in our sample space. So again, the sample space is just a set, right? Or 집합이요. So our sample space or our set has a finite number of elements, or it can have an infinite number of elements. Right? So depending on these two, we call the finite case as discrete random sample space, and then in the case of an infinite case, we call that as continuous sample space. Okay. And then now we categorized our sample space into two, discrete and continuous. And then each of them has their own probability distribution. So in the case of this, so our random variable x and their probability value, and then we can consider this another function that maps this random variable into this probability value. Okay, so in this case, so we can consider another function f of an x that indicates the probability of each random variable value. So we have two different random variable value, and then and their probability value will be 0.5 and 0.5. Okay. Okay, and then let's just recall or remember what we learned in the previous semester. So in this case of function, what was this set called in this function? 이게 뭐죠? 한국말로는? 펑션에서 1대1 뭐 함수 1대1 대응 뭐 이런 게 있었고, 이거 우리가 so 이렇게 불렀죠. 정의역. Then in English it's called domain, right? And this is called what? Codomain, right? And then those values that actually gets hit by this arrow were called image, right? Image. Okay. Okay. In this relation, in this properties of the function. So in order to call that, in the world of probability, this function that indicates the probability of each random variable value, this probability function has to satisfy some properties. And those properties are not that difficult. It's quite easy one that you probably already know. So each of these values in our image or codomain, so each of these values should be always non-negative. So they should be greater than or equal to 0. And then if we sum up all the elements in our image, and then the summation should be equal to 1. Okay, and then the meaning of this function f, here we call that as p because we are talking about the probability. Okay, so we specifically named or gave the name of that function as p. Okay, so p of x equals to x is the same as this function value f of an x. Okay, and here in this case, what is the capital X and what is the small x? What's the difference between them? 차이가 뭐죠? 이거 x랑 small x랑? 네. Real number? So this is a random variable itself. So for example, something like this. In this case, this height, so this is an height. So this height itself, and the notion of this height is our random variable x. Okay? And then specific value of 180 centimeter. So this specific value is represented as this small x. Okay? So although it doesn't look like making much sense, like x equal x, right? So it does not make much sense, right? But in this specific case, so you have to understand the meaning of large x, the main difference of large x and small x. Okay? Okay, so these three were the requirements for this probability function, and specifically that is called this probability mass function. And then we consider this a cumulative distribution function or probability function, where we instead of just height being equal to 180 centimeter, we can consider all the probability of height being equal to or less than 180 centimeter. Okay, so in this case, we are actually accumulating or summing up all the probability of height being equal to 180 or less than 180. So that is called this cumulative distribution function. Okay, and then mathematically we can represent this form in this guy. So ft, what was ft? So this was this guy, probability function, or probability mass function, or probability distribution. Okay, so we sum up all these values when x is less than or greater equal to x. Okay. Okay, then this is an example of probability mass function. So when x is 0, 1, 2, 3, and 4, so they have these non-negative probability values, and summing up all these values, they should sum up to 1. And then they can be represented as this histogram. Instead of just a point, we can make them as this bar graph. Okay, so that is called this probability histogram. And then we can think of this cumulative distribution function. Okay, so in this case, probably you have seen this type of function where we have like discontinuous points. So these are not connected to each other, right? So they are disconnected at this point where x is 1, okay, and also x is 0 and 2 and so on. But in this case, so we learned about this part. So filled circle and empty circle. Okay. So in this case, in this particular case, even though they didn't represent this empty circle, but this is the same as this empty circle at this point. Then, when the probability changes, this type of pattern is always true. So it always happened in this exact same way. Okay, which means the circle, the filled circle is at the top, and then the empty circle is at the bottom part. And the reason is because our probability, our cumulative distribution function has this inequality sign as less than or equal to. Okay, so this equal means we always contain the value x itself, right? So at this point, so we are containing, or we are including or adding the probability of x being equal to 2, right? So that way the probability suddenly jump up, and then the actual function value for this cumulative distribution function will be 3 over 4 instead of this something like 3 over 16 or something, right? Okay, and then the next thing is a continuous probability distribution. And then the continuous probability distribution, so the main difference between the discrete and the continuous random variable is that in the case of discrete random variable, we consider the probability mass function. But in the case of continuous random variable, we consider the probability density function. So instead of mass, we use the term density. Okay, So the reason for using this density instead of mass is that, so suppose this random variable of height, and then is this random variable a continuous one or discrete one? Is this discrete or continuous? Yeah, this is a continuous, right? So when considering the probability of height equals 180 centimeter, what will be the probability of this value? It should be 0, right? So so someone might claim that, oh, okay, I'm exactly 180 centimeter tall. Okay, so yeah, I'm actually existing, so the probability of being 180 is not 0, right? But in this case, we can think of the situation as like, so you pick up whatever person that you pick up, and then all these people are claiming that they are 180 centimeter tall. Okay, but their really exact value of height might not be exactly the same as this 180 centimeter. Okay, so they might be 180.1 and 179.9995 and so on. So that way, it is almost zero probability to find out the person that is exactly 180 centimeter tall. Okay, so that way we can understand this this equation in this manner. But still, in this case, we can think about the probability density. So density means like around the region of this value, roughly how much the probability is located in this part. Okay, so in this distribution, this part, so when talking about the Gaussian distribution or normal distribution, this type of like mountain-like probability distribution is actually the probability density, right? So in this case, even though we can say that 170 centimeter and 180 centimeter, the probability density is much higher in the case of 170 centimeter compared to 180. So this guy is larger than this guy, right? But in this case, the actual probability of being 170 and 180, they both are equal to 0. But in terms of density, so roughly within this small regions around 170 and 180, their probability will be higher than this guy. Okay, then this density can have a really diverse shape like this and this and this and so on, right? And then from the density of continuous random variable, we can think of this probability which is actually non-zero. So for example, like 160 centimeter in height and 180 centimeter. And then this probability is now non-zero value. For example, like it could be 0.7. Okay. So this is actually the probability, and that probability is computed as the integral of the area of this function, of probability density function. Okay? And then just like a probability mass function, this probability density function in the case of continuous random variable should satisfy some property. So the first property is that the density should be always non-negative, which is greater than or equal to 0. And then their integral over all the possible x values should be always equal to 1. And then this probability of x between which have the value between a and b, they can be computed as the integral of this probability density function between the range of a and b. And then similar to cumulative probability function, we can think about this cumulative distribution function or cumulative density function for continuous random variable. Okay, so in this case, instead of being height being equal to exactly 180 centimeter, we can consider the probability of height being equal to or less than 180 centimeter. And then in this case, it's just integral from minus infinity up to 180 centimeter of this function of probability density function for our height. Okay. And then in terms of plots, this cumulative distribution function can be represented in this form. Okay. And then next topic is joint probability distribution. So joint probability distribution actually involves two or more input variable. Okay, so in the earlier case, we only considered like the rolling of dice. In the case of dice rolling, 1, 2, 3, 4, 5, 6, and then suppose these are random variable that are already enumerated. Okay, so these are random variable, which means or which indicates the dice value itself. Okay, so in the case of an event space, and their outcome is actually the situation of seeing the dice value of 1. Okay, and then we can map this event or this outcome into a numerical value, or really the number. Okay, so suppose that number is just a dice value as this guy, and then we can now call that as random variable x. And then their probability can be considered, or probability function or probability mass function can be considered as this form. So it should be 1, 6, and then this guy, interestingly, 2, 6, and this guy is now 0 and 1, 6, and so on. Okay, so we made up a special dice so that their probability has this type of a distribution. Okay, so this was the previous basic form of probability function. But now, when talking about this joint probability function or distribution, we involve two or more variable. So our outcome or event space is actually involving two events or two outcomes at a time. So we roll a dice, and also we flip a coin. Okay, and then in that case, all the possible outcomes can be listed as, so this is a coin and this is a dice, and this can be head and 1, 2, 3, 4, 5, 6, right? And then tail will also have 1 to 6, all these different cases. So altogether, we can consider the function of, so this one, let me rewrite it. It is head and 1, head and 2, head and 3, head and 4, 5, 6, and tail and 1, tail and 2, and so on. And then each of these events will have some random variable x as maybe, so it should be some kind of enumerated version. So it can be 1, 2, 3, 4, and so on. So in total, we will have 12 different cases for this random variable x, and then this guy will have some probability. Okay, and then from this joint, in this case, let me just explain it again in this different way. So C is mapped into a random variable x, and D is mapped into a random variable y. So H is mapped to 1, and this dice value 1 is mapped to 1 for the random variable y. Okay, so 1 comma 1 will have a probability of 1/12. Okay, and 1 comma 2 will also have 1/12, and so on. But here, this mapping is called disjoint probability distribution. So this is actually mapping x comma y as a pair, right, for our input, and then this guy will be mapped to a certain probability value, right? So that way we can extend or we can increase the number of random variables in the input side. So that is called this joint probability distribution. And then this joint probability distribution should satisfy these equations. So they should be non-negative for all the values of an x and y, and altogether they should sum up to 1. And then for a particular sample or of x and y, this probability is the same as this joint probability function f of an x and y. Okay. So this is one example. So altogether, this is all the mapping relationships. So this table is actually the function of f of an x and y. So depending on the value of an x and y, their probability is represented in this form. Okay, and then the summation of all these values should be 1. And then these values are the summation of the 3 values in the same row. Okay, so in this case, those values will also sum up to 1 because each of these 9 elements should sum up to 1. So these values are the summation of these 3 values, and these values are the summations of these another set of 3 values. And so altogether, summing up these 3 values should be always 1. Okay. And also we can consider this column sums. So we can just sum up those values per each column. Okay, so so this is a joint probability distribution or joint density. And then those values, for all these values, even though x changes from 0 and 1 and 2, but in all these 3 cases, y still remained as 0, right? So this is actually the probability of x being equal to 0, right? And this is x being equal to 1, x being equal to 2. So, yeah, collecting those information, we can consider the function of the function that maps different x values into these probability values. This should be y, right? Because all these 3 cases will have the common value of y as 0. So it should be y. And then this can be viewed as the probability of just y, right? Regardless of x. So even though x and y happening together, okay? So for the same value of an y, they can be different values of an x. So they can be there can be many different cases. But by summing up all of them, we can consider we can think of the probability of y being 0, and then y being 1 and 2. So for this probability function, or this function is called a marginal probability distribution. Then these values will represent the marginal distribution of this guy. Any questions? Okay, back to this joint density function. This joint density function should be always greater than or equal to 0, so which means they cannot have negative values, and then the integral or the summation of this function over all the possible x and all the possible y values, and then their probability will be always summing up to 1. Okay, so in the previous case, summing up to all the values for all the possible x and y values, all these different values will be just equal to 1. And then, the interpretation or the actual meaning of this function is that the probability of A of x and y belonging to a region of an A, that is, doing the integral over this region of an A on the function of this f of an x and y. Okay, so in this case, in the previous case, let me just give an example. So in the case of joint density or joint probability distribution, so we have to consider x and y simultaneously. So suppose x x is height, and then y is maybe gender. Okay, so x is, or height is 170 and 175, and also y should be maybe female. So altogether we can consider the probability of this joint event of height being in this region, and also y being, or gender being, female. Okay, and then we can just find out those values from this probability table that matches these requirements or condition, and then we just collect all these values satisfying this event or this condition, and then we just sum them up, and then that probability will be this value. And then in the case of continuous random variables, we have to perform the integral, right? So we have to perform some integral like height being 170 and 175, and integral doesn't make sense for this discrete random variable, so let's change that as weight. Okay, so the weight should be like 70 kilogram up to 75 kilogram, and then among these regions we have to perform these integral in this manner, so that way we can compute the probability of this event. Okay, and then this marginal distribution is what I briefly described in this table. So this part is the marginal distribution of y, and this part is marginal distribution of an x. So the meaning is that even though x and y happening together, we only consider y regardless of an x, and then we consider the probability of y being 0, and then this probability will be summing up all the probabilities of different x values, but still y being the same as 0. Okay, so that way we compute the probability of y being 1 regardless of an x. So such type of probability distribution is called this marginal distribution. And then mathematically, given this joint probability distribution, we just sum them up over all y values. And in the case of continuous random variable, then we perform the integral over y when computing this marginal distribution of an x. Okay, just to give you just another example and understanding of what the marginal distribution is, let's just consider some joint yeah, joint distribution like this. Yeah, not sure if it's a good example, but oops. So let's consider we have two random variables of an x and y. So you can consider this x-axis as just a height and the other as weight. And then their probability distribution can have this type of shape. Okay, so in this case, this is our joint distribution. And then the intuitive meaning or the process of computing, for example, like a marginal distribution of an x. So this is an x, and this is a y. Then the process of computing the marginal distribution of this x. Okay, so we have to remove y because we do not care what the y value is. We only care about the value of an x. So in this case, we have to sum up all the probability values for all the possible y values. So in the previous example, consider the probability of x being 1. So 1 is around here. And then we fix 1, and then all the possible cases for all the different y values, while fixing x still as just 1. So x still be the same. In that case, we can consider like a little bit of this type of shape. So in this case, so we fix y value, and then we just added all the values of different x values. So that's how we computed this value. So in this case, we fixed x, and then all the density value of all the possible y values should be summed up, right? And so these the process of summing up all the different values can be represented as an integral. Okay, so integral of this function that is shown as the surface when cutting down this shape. Okay, so we basically sum them up, these functions, right? So intuitively, it can be viewed as, so suppose you fill up all these waters. So basically, the integral is computing the area, right? And then the area can be represented as all the water that we fill up below this mountain. So this mountain is filled with all the water. And then we just squeeze these values along the y values. Okay? And then the waters along this surface will be squeezed or summed up into one single value. Right? So that value will be our marginal distribution over x value. Okay? So when x being 1, then all the waters along this line will be summed up. And that amount of water will be representing the probability of x being 1. And then what about x being 0? And then we do the same thing, but we do a different cut. So we cut at a different position. And then this surface will have a different amount of water along this axis. And then all the amount of all these water along this axis will be summed up, and then that value will be representing the marginal probability value of x being 0. Okay, and then that was the marginal distribution, and also, we learned about the conditional distribution. Okay, so conditional distribution is the shape when cutting this mountain. Okay, but that shape, let's see. In this specific case, when cutting along this direction by fixing x as 1, that shape may not be summing up to 1. So that shape is, I mentioned that shape as conditional distribution. So in that case, we can consider the conditional distribution of y given x equal to 1. Okay? But in this case, this may not, the summation of this particular function may not be 1. Okay? But in this case of conditional distribution, we have to satisfy, or this conditional distribution should always sum up to 1 in order to call that as the probability distribution, right? So intuitively, when cutting this mountain at around this point, and then the overall height is a little less compared to the case where we cut them at this point, right? Overall, when cutting this part along this line, and then the mountain or the shape is relatively higher than the case where we cut this function at this point, right? But in order to call that as the probability distribution, we have to normalize them. So we have to make all the areas under this mountain be always equal to 1. Okay, so that way we have to normalize this function in a way that this guy is 1, okay? So that guy is, in order to make this equation true, we have to divide this guy into this form, okay? So again, yeah, let me explain it in this way. So initially we are given this joint probability, and then we fix x being equal to 1, okay? And then that is the surface when cutting this mountain, right? And then that mountain will not sum up to 1, and thus, in order to create this guy, which is a marginal probability distribution, we have to normalize this guy by this guy. And then, since this is also a density or continuous random variable, this p is changed into the density function f. And then this density is, how can we compute this value? How can we compute this value? This value is computed in this form. Okay. So what is this value? So this value is, so before considering this, let's consider this guy. So given joint density f of an x and y, we sum up all the possible y values. So that means we are squeezing these mountain, right? So that way we will obtain the function, the function of an x, because we removed y by squeezing the function along the y-axis. Okay, and so this is our marginal distribution, and then this function will give you the function value when x is 1, right? So this function value is actually is actually added to this denominator part when computing this marginal distribution. So intuitively, so from this function, so we first cut them, right? And then we just adjust the shape of this function so that the area under the function to be equal to 1. Okay, so we either increase or decrease this function so that the integral or area under this curve being equal to 1. Okay, and then how much should we increase or decrease? And that value is determined by this normalization value of this guy. Okay, and that guy is actually not a separate one, and that value is just the original integral value or original area of this shape after cutting this part. So suppose the result of cutting process, the surface or the shape of the function along this cut surface was something like this. Okay, and then this area is only 0.7. Okay, so we just computed this integral along this function, and then the area was shown to be 0.7, and then we just simply increase the height by 1 over 0.7. Okay, so approximately 1.3 times higher than the original height of this function. And then that function will give you the the correct marginal probability distribution. Okay, so this was a continuous case, continuous random variable, right? So in the case of discrete random variable, I'll give you exact same example, just similar to this one. Okay, so suppose some product. So for example, like this kind of MacBook was manufactured in 2 different countries, like China and Korea. And China is producing like so China is producing like 60% of all the MacBook, and Korea is generating 40% of the MacBook. Okay, and then the this MacBook can either work great or it can fail. So it may be just faulty, and then it stops working. Okay. So it may be this faulty, and it's okay product. So it's working well or not. Okay, so there are 2 different cases, right? So in this case, China and working great. Okay, in this case, the probability was overall 0.12. So for example, China produced like 40%, and then working great, the probability of that is 30%. And this is actually the conditional probability of this guy, right? And this probability is 0.3. And then altogether, it was manufactured in China, and then it works great, and the probability of it is 0.12. Okay, and then China, and then okay, for this probability, it's somehow 0.31. Okay. So in this case, it should be 70. So 40 times 70 should be 28. Okay, it should be 0.28. Right. So in this case, these 2 cases are the joint probability when the manufacturing location was fixed as China. Okay, but in this case, suppose we don't know this 30% and 70% at all, and then we only are given these 2 probability of this joint event of being China and working great, and China being faulty. Okay, and then in this case, in order to normalize these probability between 0.12 and 0.28, and then their sum is 0.4, right? So we have to, so in order to make this guy as correct marginal probability, we have to divide these values by 0.4, right? Which is the total sum of these two values. So divided by 0.4 and 0.4. And then this value will be 30%, and this one will be 70%. Okay? So that way we can recover this correct marginal of 30% and 70%. Okay? So these 0.12 and 0.28 was given from your joint distribution. And then in order to compute this marginal distribution of 30% and 70%, we have to normalize these values so that all the possible values of these values to be 1. Okay? So dividing by 0.4 is actually the same as dividing by the area under this curve. Okay, so that the area is 0.7. So yeah, we divided these values by 0.7, which actually increases the height a little bit on this function. Okay, and then now the statistical independence. So we learned about the independence. So what was the definition of an independence? It was something like this. So x and y are happening together, but the probability of x happening is the same as probability of x happening given y. Okay, so so we consider the region and a person's height. Okay, so this is the region where you are living in, and then another variable is height. So p of height being equal to 180 centimeter is actually the same as p of height being 180 given region equals Seoul, or the same probability when region changes to maybe Daejeon. Okay. So for these conditional probabilities will be always remaining the same as just probability of height being 180 regardless of the region. In that case, we can represent that relationship as this guy, and this is the definition of statistical independence. And then in terms of a continuous random variable, it can be rewritten as this guy, f of an x, and this guy is f of x given y. Okay, so in the case of a statistical independence, we have to satisfy this. And then let's just consider just a typical joint distribution or joint event of x and y. And then we can put some order. So suppose we generated y first, and then given a particular y, we generated x in the next stage. Okay, so this joint probability can be represented in this form. But here in this case, when they are statistically independent, then this part can be written as just an f of an x. So in this case, f of y, and this becomes f of x. Okay? So this is the definition of statistical independence. Okay. Okay, and then let me just explain a little bit more about their intuitive meaning using the same joint probability function. Let's see. In this left case of function, so in the case of left function, do you think this is statistically independent between x and y? Is it or not? If not, why? 왜 이게 아닐 것 같아요? 네. 다시 한번.
달라지면 y가 같이 y y의 그래프만 보면 x가 달라지는 걸 따라
높이가 달라진다. 네, 그것도 좋은 지적이에요. 높이가 달라진다. 근데 거기서 이제 하나 더 생각을 좀 해봐야 되겠는데. So yeah, the student mentioned that. So since depending on in the previous case, we consider the conditional probability, and then those conditional probability should always remain the same. So which means the probability distribution of height, a person's height, depending on the region, should be always the same. So basically, the distribution of height within Seoul and Daejeon should remain the same. Okay. So suppose this guy is region and this guy is height. So height has a little bit of nice distribution like this. So suppose so when talking about the conditional distribution, so we fix the region as Seoul, and then we consider this guy, and this guy, and this guy. So we consider 3 different cases. So this guy is Seoul case, and this guy is the case of Daejeon. Okay, so they can be still the same. But what about this guy? P of height being 180, or this probability. So this one was just a simple example, but we have to remove this part because height, the probability, when the height is 180, it should be satisfied, and also height should be 170, it should also be satisfied. So it should always be true regardless of the height value. Okay, so altogether, when removing this part, it gives us that. It gives us the requirements that this marginal distribution being the same as these 2 conditional distributions. Okay, so from this graph, what is the marginal distribution? So we only considered 2 different conditional distribution when the region is fixed as Daejeon and Seoul, right? What is the marginal distribution of just the height regardless of the region? So we have to sum all the different regions, right? So for a particular height value of 180, for example, we have to sum up all the possible cases of the regions, whether it's a Daejeon or Seoul or Gyeonggi or any other, right? So intuitively, that is just squeezing these mountains along this direction, right? So we squeeze this direction, along this direction of this mountain, right? And that distribution, after squeezing them up, all the water height is actually our marginal distribution of height, regardless of the region, right? And that marginal distribution, after we just squeezing them up, that distribution should still be the same as this surface after cutting at this point, and even after summing them up. So all the 3 different cases should always remain the same. So that is the meaning of the statistical independence. Does it make sense? Okay, and then back to this equation. Their meaning, the meaning of this is this guy. So it boils down to this equation. Okay. Okay, so if we have more than 2 variables, and then the same statistical independence is extended in the exact same manner. So this guy is represented as this. Okay, but yeah, let's just consider the joint probability distribution of this guy, x, y, and z, and then yeah, in terms of so when fixing the order as A, B, and C, and then this joint probability can be written as this guy, f of an x, f of y given x, and then f of c given x comma y. So both x and y are fixed, and then z are generated, right? So in this situation, this statistical independence says it should be, this guy should be just f of y, and this guy should be just f of z, which is just a marginal distribution when only considering each variable, right? Without just considering any other, right? So when satisfying these values, okay, and also, in other words, when we have x, y, z, w, or even more variables, okay, if they are all statistically independent, and then this equation should be always true. Okay, so this is a star, and this is maybe a triangle. Okay, so this star should be just one variable out of the variable that you have. So it could be x or y, z or w, but it should be only one. Okay, and then this part, you can put whatever other variables that you have at this position, and then for all these cases, this equation should always be true. And that's only when, only after then, we can call them as statistically independent. Okay, so that's it for chapter 3. I wish I could, go beyond at this point, even up to some part at chapter 4. But we will not have a class this Wednesday, right? It's Thanksgiving, Korean Thanksgiving. So let's meet next Monday, okay?